Okay, welcome everyone. Good morning. So let's start our WeldGalaxy Innovation Day. Thank you for joining. The agenda today it's quite exciting. Okay, so first we'll start with the introduction about the second WeldGalaxy Open Call, because as you know, now this opportunity for Weld innovators is open. So I'll tell you a little bit about the rules, and so you can check actually if you're eligible. And then after me, Geoff Melton from the Welding Institute will share with you more details about the technical support and the requirements. So I believe that will be even more interesting part for you. And after this short introduction about the second open call and the rules, then we'll have a short coffee break, and after that you will be able to meet the pilots that were selected in the previous open call that was launched last year. And actually they are now on the, well, they just finished the support program, so we have invited all of them to present their pilots, their progress, and yeah, so you can see actually what are the real benefits and outcomes of WeldGalaxy Support program. So first, starting from myself, from introducing myself, I'm Isabella Zrazinska, and I'm the Senior Project Manager at FundingBox, who is managing the open call in WeldGalaxy as well as the business support. Okay, and I have with me Geoff Melton. I'm sure Geoff, hello.
Hi.
The project coordinator of the WeldGalaxy and technology manager at TWI, who, as I mentioned, will present later. So there will be opportunity to introduce yourself in more details. Okay, so starting from the WeldGalaxy as the word of introduction for those of you that that haven't heard about the project. We are already working together since 2 years. Okay, it's a consortium of 11 partners that the main goal of the consortium of the project is to create the online platform for the welding industry that will bring together the global buyers and sellers for the welding product and services. The consortium is led by the Welding Institute, one of the leading institutions in the welding industry, and it gathers many other players that, well, each of the partners is working on the different functionalities of the platform. We have the Universidad de Madrid, the Politécnica de Madrid, we have Lula University of Technology. So there are a lot of players that support this. And well, as I mentioned, FundingBox is, and well, in the case of the support program that I will tell you a little bit more about, you should pay the attention to TWI, of course, who will provide the technical support, and FundingBox, which is will provide the business support. But of course, the rest of the partners are equally important in this project. Then about the benefits, so if you get accepted in this second open call, we are looking for 15 pilots that will be funded with up to 100,000 euro per pilot. And if you get accepted, you enter to the 6-month support program that is led by TWI, which is leading the technical support, which I believe is the most important part. And Geoff will tell you a little bit more about what is actually under this definition. The program is divided in 3 stages. The first one is the kickoff, so that's where you work with your technical mentor on the individual mentoring plan. Then you will enter to the longest phase, which is the implementation, that is focused on on technology development. And the last one, the technology support continues, but you will also receive additional support with the business mentoring, where FundingBox will assign you the external business mentor that will be defined and matched according to your needs, and who will help you to define your business model, also to network, to connect with the market. And of course, on top of this technical business support and funds, you will also receive the access to WeldGalaxy account. Okay, so this is important that those selected pilots will become testers of the platform. So This is also part of the program to support the innovations, but also to engage those innovators in the main goal or the main result of the project, which is a WeldGalaxy platform. And of course, media exposure. So by being a part of this European initiative, we make all possible to make your success story visible. And also, well, if possible, also to help you with the further funding when the project ends and support ends. And so benefits are multiple. And who are we looking for? So what is important is to remember that we are looking for the Ark welding solutions. So it is also the specific part. And of course, for the solutions that are disruptive, innovative, that actually bring something to the sector. But I think this will be also commented further by Geoff, but what is important here is that it could be either process, okay, or it could be also equipment and consumable, okay. So there are different ways if you think about the innovation, that it doesn't have to be exactly only the equipment. The processes could be also innovative as well and bring a lot of innovation and disruption to the sector. From the legal point of view, we accept the proposals. You can apply as a single applicant, as a single company, or as consortium. Okay, so, but what is important to take into account is that your company need to have an SME or mid-cap status. Okay, so at least one. If you apply as the one, you need to be the SME or mid-cap. If you apply as the consortia, then at least one company needs to be SME or mid-cap. Okay, and if that is a new definition for you, so just to let you know that how to evaluate that or how to assess if you have this status. So you have to check your headcount and annual turnover and check the limits that are included in the guide for applicants. Okay, you can also check the European rules for that, but these two elements are the core when assessing this part. And also don't forget to check, because sometimes it's also, well, I would say not that clear, but if you're a subsidiary of a bigger company or you partner or linked enterprise, that is also important. Okay, so don't look only on your company, also see all the connections that you have, because sometimes they influence. But in case the status, but in case you are not sure, always feel free also to contact us and we can also help you, okay, before you apply. So this is in short. As I mentioned, well, the scope, which is Ark welding, and also technological challenges that were predefined by the consortium, and you need to reflect on at least one. I didn't comment much on that because this is a technical part that Geoff will tell you a bit more. You also need to remember about the technological readiness level that has to be, the minimum is 5. Okay, so your technology needs to be already well in some relevant environment. Okay, so this is not like from the idea, you need to already have some concrete development, but we want to help you, of course, to raise more. And from the legal part, minimum one SME or mid-cap. And of course, this open call is also dedicated only to European, to the companies registered in Europe, associated, and United Kingdom. And yeah, so that's the eligibility. For the selection process, it's also quite simple, even though you see a lot of things on this slide. But I think what I would like to focus here is the experts evaluation, okay? Because of course, eligibility, that will be the standard check on the country, or on the standard criteria that I commented to you before. But then the experts evaluation, that is actually where the real evaluation happens, because the external experts from the industry will read your proposal and will score it according to their potential and to the scored sections that are the excellence, impact, and implementation. Okay, all the rest are more administrative part, but also you need to fill it out. But these three are the most important when you will be preparing the proposal. And basically the excellence is about your technology innovations. So you have to show the state of art of the technology that you like to develop in the support program, and also include like try to reflect on the technological challenges, okay, that are predefined by the consortium. So you have to try to reflect on that in the excellence section. Then in impact, we want to see what is the reach of this technology. So what is the scalability? If you are able to show that it is applicable to different industry, that is actually means that it's scalable. So the impact on the market, your competition, if there is any, your business model. So that all that should go to this impact section. And also, of course, as always in the European programs, there are also questions about the equal opportunities, social impact, and environmental impact, okay, which are the additional, but also very important. And the last one, the implementation, which I believe is also the most difficult one, because this is where you have to plan actually what would you like to do during this 6-month support program. Okay, so that is where you have to include the main tasks, of course, in the generic way, but it has to be clear what do you want to do in this, what's the pilot, okay, what do you want to test and develop, also what support you will need. And that is also where you should include information about the budget. Okay, so you need to tell us more or less what plans or what spendings you have, and of course following the very easy division. So it will be the personal costs, travel costs, and also consumables. Okay, so this is the standard one for European programs, but if you have problems, of course, everything is included in the documents for the open call to help you to prepare that. And the exact definition of each of criteria is included in Guide for Applicants, section 4.2. So also we invite you to read that before you start filling it out. And yeah, this is more or less in short about the open call rules. If you need any help, we have of course, you can write us an email. You can also, we have like the community where you can ask questions in public. But of what is very important before we decide to apply, please read Guide for Applicants. We try to make it simple and clear. So this is very important to start from that. Then you can go and start filling the application form, and if you have any doubts, you can check the frequently asked questions document, or you can also watch one of our webinars from the past or in the future, because we'll have the final one at the end of March and the end of April, sorry, where you can actually like ask the final questions. Okay, so this is also the support. And you're invited to join our community where we share all the updates about the project, about the industry, and for now, mostly about the open call. And forgot to add, to apply before 29th April. Okay, so there is still 1 month to prepare the proposal. Here is the link and our email in case you have any doubts. And yeah, from my side, that's it. And I pass the voice to Geoff, who will tell you a bit more about the technical side. And I forgot to add.
Okay, thank
you. Yeah, Geoff, sorry. If you have any questions, please write them in the chat. And after Geoff's presentation, we'll have a small Q&A. That's something I forgot to add. That we don't have Q&A now. We'll leave it for the end after Geoff's presentation. Sorry, Geoff, up to you.
Okay, thank you very much, Isabella. So it's now my turn to talk a bit more about the technical side of WeldGalaxy and the Open Innovation calls. The first technical hurdle I have is to actually show my screen. So let me see if I can do that. Okay.
Yes, we can see your screen, Geoff.
You can see the screen, excellent. Well, thank you very much. The technology works. Okay, well, good morning, everyone. I'm pleased to see so many people who joined today to listen to us talk about the WeldGalaxy project and the exciting launch of the Open Innovation calls. I'm going to talk a little bit about, very briefly, just say a little bit more about myself, about TWI. I'll then say a little bit about the WeldGalaxy platform and the overall project, and introduce you to that, and then move on to talking in a bit more detail about what we're looking for in the Open Innovation calls. So just by way of introduction, this is me. I'm the coordinator for the WeldGalaxy project. I'm also a technology manager at TWI, and I've spent most of my life in welding research, development and support, both at TWI and also as a principal engineer for one of the leading manufacturers of welding equipment and consumables. I'm currently also the chairman of Senelec TC26, which is welding equipment, standardization of welding equipment. I'm the chair of the IIW Commission 8, which is on health, safety and the environment. So this is very much my background, and I'm here to support the WeldGalaxy project, and also those of you that are successful with your proposals for the Open Innovation Call. So one slide about TWI. This is TWI. Our headquarters is in near Cambridge in the UK, but we also have offices around the world. We're a membership-based organisation, so many companies join us. They pay a subscription fee, technology access fee, and for that we carry out contract research for them, support in production or the development of their innovations. But we also are involved in many collaborative projects, such as WeldGalaxy. We are a company which is limited by guarantee, so it means we don't make a profit. All the profit that we do make through our work goes back into funding our facilities and our resources. And this is a picture of the new buildings that we've had built over the last 10 years, basically, as we've expanded. And we now have about 700 people, a turnover of 70 million. I'm a physicist, so these are very round numbers, but that's roughly the size that we are. As I say, we provide services basically to the welding industry in joining processes, inspection and training. So we're here to support the Open Innovation projects, and myself and a group of us here will provide that support to you. So I'll just say a little bit about the WeldGalaxy project itself by way of introduction. I think it's important to understand what the overall WeldGalaxy project is about. It's a 42-month project, and as Isabella said, it's to develop a knowledge-based platform for welding to facilitate business-to-business transactions. And I would like to stress it's all to do with using knowledge to make informed decisions about how to weld something, which then leads to the equipment and consumables that you need to do so. So I approach WeldGalaxy very much like we do at TWI, as we have we call a duty engineer, whereas a qualified engineer is on duty every day to answer our members' questions and to help them make decisions about how they will weld things. So we very much, that's the interface to the WeldGalaxy platform. You come into the platform and either through the chat bot or directly into the platform, there is a discussion about what the requirements are. What is the material that you intend to weld? Is it an aluminium? Is it stainless steel? Is it a thick section or is it very thin? And what standards and codes are you working to? Is it an aerospace application, maybe a welding thin nickel alloy, or are we talking about a heavy construction such as a bridge in structural steel? So then we can draw upon the knowledge we have that's in the WeldGalaxy database and make selections in terms of what process should be used, what consumables should be used. And then the database contains information from the suppliers of those products. So through what we call the KBE, the intelligence in the database in the platform, we will select suppliers of those products and then introduce you to those suppliers. And there are other aspects too. There are tools on the database for predicting distortion, doing life cycle analysis, etc. So many aspects to the database, but I said it's all to do with coding knowledge, taking that knowledge from TWI, from equipment and consumable manufacturers, and coding it in a certain way so that it can be accessed in the database. And here we are. This is the WeldGalaxy platform. So on the platform we have knowledge pages. You can go on the platform and you can look up information about products and processes, information about products, and also tools in terms of to help you make those decisions in terms of process selectors. There's a tool to look at distortion, so another tool to look at health and safety and environment aspects of the welding process. It's accessed through either through the chat box here or directly through typing information into the platform. This is the realization in the nice WeldGalaxy color scheme. And if we just look in a little bit more detail, we have the login, the user interface here. So our users will come into the WeldGalaxy platform. There's the selection of the process and the consumables is done here. We have knowledge pages, and go in there and find out information about various processes and aspects of welding. But then leads us through to a selection of the appropriate products that can be used for a particular welding application. They go in the basket, and then we come into the more commercial side where we have the suppliers of those products, and then we can go through that transaction, which may be quite simple, maybe just on price, or it may be in performance. It could be simply somebody wants to buy a new item of welding equipment. It could be somebody's looking to a new way to produce a product, and they need the whole production line to do so, which will be the equipment, the consumables, the robotics and sensors. So the WeldGalaxy platform offers a safe and secure way of going through that process of selecting a supplier of your products and engaging with them on a commercial basis. So that is the WeldGalaxy platform. Very briefly, and to find out more, you can go onto our website, www.weldgalaxy.eu, and that has lots of details. It has press releases, and it has a lot more detail about some of the things we're doing in the WeldGalaxy project. But now I want to talk a bit more in detail about the Open Innovation Call. So Isabella has introduced the call to you, and in terms of the call has now been launched. This is the second call that we've launched. So we're in the process of going through that selection process, or indeed the process of inviting proposals. And then we will go through the selection, and we'll select 15 proposals to take forwards as projects. And we have a group of welding experts around Europe who will make that assessment. It's not done by TWI, it's not done by me, it's done by a panel of independent experts. And so they're all looking forwards to your proposals. Last time we had some very interesting ones, which we will present at the end of this session. So what I want to do now is to say a little bit more detail about what we're looking for from the technical side for the Open Innovation Call. We're looking for innovations and developments in arc welding, and that could be quite a wide range of things, but very much innovations and developments to improve arc welding. Now, arc welding has been around for over 100 years. I always say it started with the invention of the covered electrode by Oskar Schellberg in Sweden in around, I think it was 1905, 1906. And from that very basic process of arc welding, we've developed a whole range of different processes. And those processes continue to be developed to give us improvements in terms of quality and in terms of performance. So to help you decide how to approach the proposals, we've offered some guidelines, which we call the technological challenges. And these are guidance really in terms of the sort of calls that we're looking for to take forward to fund in the WeldGalaxy project. So you see we have tools that support plug and produce manufacturing of arc welding equipment and processes, and that's one of the headlines for this WeldGalaxy project, is the capability to produce plug and produce products. But we were looking for innovations to improve welding productivity and quality, innovations in arc welding robotics. Increasingly with the difficulty in finding skilled welders, people are turning to robotics, and it's important that we have intelligent solutions that enable us to be able to replicate the qualities of a manual weld with a robotic solution. We are looking for also for innovations to support health, safety, and increasingly the environment, which is becoming increasingly important, which comes on to work in terms of something we are doing in WeldGalaxy, and we're looking for other projects to support that in terms of life cycle analysis. So I'll give you a little bit more detail.
Joss, are you here with us? Okay, so there's a slight technical problem because I think Joff has lost the connection. No, I think it's not only you, Adrian. I think it's for all of us. We'll just wait a couple of minutes, hoping that Joff can get back into the webinar. Joff, are you here with us now?
Hello, can you hear me? I'm afraid I lost my connection.
Yes, yes, we can hear you now. We can hear you now. Great to see you back. We lost Joff around 90 seconds ago. You were about to say, I'm going to give you more details on something, and then we lost you. So if you could take back from there, that would be great.
Okay. Well, thank you. Well, right, not to lose any more time, and apologies to everyone about my my dismal internet connection. It's a problem we all face from time to time. It's always unfortunate when it happens during these presentations, but I'll swiftly move on, and hopefully we won't have any more disturbances. And I'll give you a little bit more detail about the technological challenges. So the first one is systems and tools that support plug and produce manufacturing of arc welding equipment, and that is really plug and produce is something people ask me, what does it mean? To me, it means an item of equipment primarily, which can be added to a conventional welding system, whether it be a manual or a robotic system. You plug it in and it starts producing product, and it works with the existing welding equipment. So not only are we looking, for instance, as I show in the picture here, which is a novel system for looking at discrepancies in components to be welded that we developed in another European collaborative project, but also the standards that go around that. So it may be a standard interface for connecting items in a welding cell. Particularly, we're looking at innovations to improve the process. So look at improve the productivity, improve the quality of an arc weld. And certainly there are a number of innovations that have come through in recent years using developments in control in computing power and power electronics, which enable us to make better welds, whether they be using multi-wire processes to increase productivity, or giving us increased control over the welding arc to improve the quality, to reduce the spatter, to improve the consistency of those welds. So we're looking at projects that tick these sort of boxes. We then have robotics. I said robotics is increasingly becomes important for us, and developments in robotics. Particularly, I think we'll be looking for seam trackers and sensors, and we have a number of projects already in the first call, and innovations in terms of how we use robots, sensors, I say here, using artificial intelligence to tell us more about the process, developments in fixtures and fixturing, and and positioning of welding components. And you'll hear about one of the very interesting projects that we funded in the first call in that area. So we then have also innovations to support health, safety, and the environment. I think these are increasingly important topics. And indeed, there have been recent European regulations in terms of energy efficiency of welding processes. So we're very keen to find projects in this area, and also particularly because these projects need to feed into the WeldGalaxy platform as well. So we don't want to look at these projects in isolation. We want the successful pilots to engage on the WeldGalaxy platform to test it, but also provide more information and more data onto the platform to build up the knowledge that's embedded in the platform for making these decisions. So important aspects here are reducing the environmental impact of welding, particularly items such as shielding gas consumption. So we use energy efficient processes, not just from the process itself, but the raw materials that go into making a weld. And also we need to have welds. We need to have a safe and healthy environment for welding. So also innovations in health and safety are welcome in this second call. So that very briefly, and apologies for the delay there, is what we're looking for the projects for this second call. Once we choose those projects, we will start working with them, with you, with 15 projects, and we do that in two ways. There is technical support from TWI, and there are also the business mentoring from FundingBox. So I would like to, just to finish off my presentation, talk a bit about TWI support, which is an important aspect of this program that we can provide to each of the projects, is the support that we have through our resources and our qualified and experienced staff to help you develop your innovations and take them to the next technology readiness level. Here are the laboratories at TWI. So you see we have a large facility here with many items of equipment. We have a suite of robots covering different manufacturers. So we have OTC, we have Fanuc, we have Kawasaki robots, and we have a lot of mechanization, automation, but also quite a bit of manual welding that's carried out in these cells here. So we have facilities that can be used as a test bed for your innovations, and it's been difficult this last year, as you would already know. We're running the first set of projects, and it's been extremely difficult during the pandemic to organize this sort of support that we hope that we would do in the project, where companies can bring their innovations to TWI and we can work with you to evaluate and improve them. We've had to do a lot of remote working this year, relying on video cameras and another support from universities and so forth. But hopefully by the time we get to the stage of working with the second core of projects, then we'll be able to have some form of support from TWI. We have been able to do that in some respects in terms of having equipment sent to us, which we've tested. We've provided results back to the projects, but I hope that things improve towards the end of the year, and we can have a lot more interaction with you. But you see we have a whole range of processes here, from basic manual metal arc welding through TIG, plasma, MIG, mag, and submerged arc, and all these processes are available in our laboratories for you to test your innovations. We also can provide a lot of expert support. We have, as I said, we have around about 700 staff. I have to say I haven't seen most of them over the last year. I've been sitting at home in my home office, but work has continued in our laboratories. And of course, we now have Zoom and Microsoft Teams, so we carry on working. But we have lots of experts in terms of welding engineers, welding process specialists, experts on robotics, experience in materials. So we have a group of material engineers on both ferrous and non-ferrous alloys. We have good NDT facilities and inspection, and certainly we've used this section to support the projects that we're running at the moment. And also we're considering doing a lot of additive manufacturing, have facilities for additive manufacturing, arc welding, which includes TIG, plasma, and the MIG-MAG process, and we have the process experts there as well. And as you will hear, we've done some interesting novel work in terms of additive manufacturing. So not only do we have the experience, we have the resources, and we have the people, we also have a library on site, and we have a number of information scientists, and they can provide support in terms of literature reviews and other information that may help you develop your innovations, as well as all the information on the TWI website, which includes technical articles, best practice guides, knowledge summaries, etc. And much of this information is actually being embedded into the WeldGalaxy platform as well, and this is available to you throughout the duration of your projects. Another aspect, perhaps not so much technical, but also is looking at the market for your products, and we can work with FundingBox and our business industry sector managers in looking at the market for your innovations. And at TWI, we cover all those industry sectors, and we have industry sector managers for each, whether that be for construction engineering, which covers aspects such as bridges and trains, aerospace and automotive, which is self-explanatory, energy and the environment, which spans a whole range from nuclear power through to wind and wave technology, electronics, photonics, and medical, which also increasingly is looking at joining technology for electric vehicles and batteries, which is an increasing part of our business, and perhaps that's taken over a bit from what would be our traditional core industry sector, which is the oil, gas, and chemical, which of course, as we all know, is in decline at the moment. And then last but not least, we have the equipment, consumables, and materials sector, which is very much focused actually on most of what we're finding in these projects, which is actually equipment and consumables designed for welding. And so we have a whole sector in that area, and that includes most of the major manufacturers of welding equipment, consumables, and robotics. So each of these industry sector experts are also here at TWI and can help you looking for the right market for your products. Okay, sorry about the brief intermission in the middle of my presentation. So that's my introduction to the Open Innovation Call, and we're really getting excited and looking forward to seeing your proposals and going through that evaluation process, and in the medium term then starting to work with you. It's now time for a short question and answer session. We will then, after the question and answer section, have a short break, and we'll come back at 11 o'clock CET, when we will get presentations from each of the 10 pilots we're funding at the moment. So Paul, I guess I hand back over to you at this point.
Yep, absolutely.
And, we'll see if we have any questions for us.
Yeah.
Thank you.
There's
I'm turning my camera back on. Hopefully
Okay.
it'll work.
Yeah,
okay,
no,
just people can see me. So, do you want to take my presentation?
Yeah, absolutely.
Okay.
And no problem at all regarding
Okay.
that technical incident that these things happen. So we've got a first question from Mario. Would you be considering Ark Spray process in this call?
Ark Spray. That's an interesting one, actually. Would we be considering Ark Spray? Well, we've never had any proposals for Ark Spray. It's debatable whether it's an arc welding process. I think I would say yes, in that it would be interesting to see what the innovations are. I think it's a bit borderline, to be honest, Mario, but I think it's worthwhile putting in your proposal, and we'll see if it meets the criteria as we are in the call documents.
All right. Well, Mario, if you have anything to add to your question, you're welcome. Meanwhile, there's another question here from Oscar, if I'm not mistaken. Who will own the WeldGalaxy platform?
who will own the WeldGalaxy platform? Well, the WeldGalaxy platform, as I first described, is being developed with the partnership that Isabella also described. It's being funded as a European collaborative project. The intention of the collaborative project is to develop a prototype platform. So once we have that platform at the end of the project, we will then decide upon the commercialization of it, or indeed we're working through that, business process at the moment. And at the end of the project, the platform will be, the ownership of the platform will be, a number of the partners will own the platform. Partners will have an option as to whether to join the commercialization of it or not. So that's the way the process works. So basically, it'll be the partners.
All right. Then another one from James, a UK specific questions. Will the call be open to UK consortium and UK SMEs?
Yes, of course.
All right. Then
I guess there's a bit of Brexit coming. No, the WeldGalaxy project is being funded by the EU, and there's agreements in place that the EU is still part, that the UK is still part of that process. So there is no reason why UK companies cannot apply for funding. And indeed, we will be considered in future as a third party and continue to be able to receive European funding for these types of projects.
Great. Okay. Then a question from Laura. So I might have to ask you to clarify this one, Laura. In any case, I'll read it and you tell me, Joff, if you understand it correctly. Regarding the cost contribution, could you please clarify the percentage amount that is foreseen? The total pilot cost would be around 166,000 euros for a 60% contribution. That is equal, therefore, to 100,000 euros. Is it correct?
Yeah, maybe
that sounds a rather complicated question. Maybe Isabella would like to come in on that one.
Yes. I can take this one. Indeed, well, the only rule for the budget is that indeed there is a minimum that should be dedicated to SME, but this is in case if you apply as the consortia and there is some large company or someone who is not SME, then you have to make sure that the minimum percentage, which I believe it's 60 or 70%, needs to go to SMEs in the consortium. So that is the only requirement. But if you ask for the personal months and the percentage assignment of the budget, there is no rule for that. So that has to be, well, it has to look feasible. So of course, there are these three categories. So it will look weird if you put like 60% of the budget to travel, right? So it's quite obvious that most of the budget will go to the personal costs, but we do not have any minimum or maximum for that. Okay, the only rule is to try to assign the budget mostly to SME and the mid caps, because this support is aimed to support actually those entities. But for the per cost, we do not have any specific requirements as long as it looks feasible. Okay. I'm not sure if I answered the question.
I think you have. We got an answer perfect. So it's cool. We answered. Then another question actually that I overlooked from Finn and not Oscar, sorry. Regarding the WeldGalaxy platform, what will be the cost for the supplier to have the products promoted and sold via the WeldGalaxy platform? I think this one would be more for you, Joe.
Yeah, I think that comes back to the previous question about commercialization, and that is still to be decided as to what the model will be for that. But at the moment, we're interested to talk to any company that's interested in putting their product onto the platform, and we will take into account the industry's suggestions for how we develop that business model.
Okay. Coming back to a previous question from Mario and the eligibility of Ark Spraying, the next there's a related question regarding cladding. That is not a process that I know. So would cladding, sorry, be considered too? CLDDING.
Yeah, cladding. Yeah. Well, if it's cladding using an Ark process as opposed to using a laser or another process, then yes, it would be included. So we wouldn't include laser cladding, we wouldn't include explosive cladding or any of these other alternatives. But if there was an Ark involved in it, then yes, it meets the scope of the core.
Okay, great. Then a question from Mugo. Can other RTOs get involved? This one, I guess, for both of you, Isa and Josh.
Yeah. I can take this one because it's more about the structure of the consortium if applying. So RTOs can participate, but under the subcontracting category. Okay, so you have to make sure that they can be delegated one of the tasks within the process, and it can be maximum of 15% of the total budget.
Okay, great.
I would just add to that actually, because this last year, or currently with the calls that are the projects that are running, we'd like to thank some of the other RTOs that have got involved through this subcontract process, because it certainly helped the pilots to develop their products, with bearing in mind the difficulty of moving products across from country to country, and also the difficulties in working in other countries. So we certainly have called on a number of universities and RTOs to support us in this program to enable it to be successful. So thank you.
Okay, then another question from Mario. Is there a minimum or maximum number of partners? I guess that can apply to the core for one given application.
Maximum, well, the minimum is one. Isabella, remind me, do we set a maximum? We're normally talking 2 or 3, aren't we?
No, we didn't, because we assumed that with the budget that it's quite well, it's 100,000 euro. There is also, and also to the proposal to look feasible, if you engage too many people, it will not look viable, right? So that's also kind of it comes up from the conclusion that, but there is no maximum, no.
I mean, just to add to that, in the current round, most of the projects are for single companies. There are 1 or 2 that have a partner, and as I say, we found it helpful for them to call on a partner, particularly this year. But I would say that we would expect 1, 2, or maybe a maximum of 3, and that will come out in terms of your planning. You have to submit information about how you're going to run the project, and we will take all that into account. But as Isabella said, we can't really foresee a project with more than 2, a maximum 3 partners.
All right. Then a question from Marqueta. Is there co-funding required from the SME?
Yes, I can take this one. No, not the. Yeah, I mean, yeah, Geoff. Sorry.
Go on.
Yes, no, because I guess this comes because sometimes the projects have this funding rate that it's 70%, and then the SME has to add its budget. But here, with the 100% of the budget is the 100% given. Okay, so there is the funding rate is 100. So of course you need to plan how you will spend the support with the funding. But sometimes, if there is something needed, then you might probably need to add it from your pocket. But basically, the funding should cover all the actions that you planned for the support program. So it's not required, okay, to have inputs or from SME's budget.
Okay. Then a question from Tom: will you be using independent mentors?
Could you repeat that, please, Paul?
Yeah, of course. Will you be using independent mentors? I think this one may be more for, well, actually for you, Joff, if we're talking about the technical support program, or unless we're talking about the evaluation process for the applications.
Yeah, so I couldn't catch the last word. Independent what was it?
Independent mentors, mentors.
Mentor.
Yeah.
Okay, right. Yes. No, the mentors are the successful projects will each be assigned a mentor, and those mentors come from TWI. So each project will be allocated a mentor with experience in the area of on the topic, but they are all TWI staff. Paul, I'm just looking at the time. We need to. I think we should keep to time, and I think we need a short break, and we want to start the second lot of presentations at 11 o'clock. So I'm just thinking, you know, maybe we take one last question, and then we maybe come back to them at the end or something, or we get back to them individually.
Let's take a break now. There's just a couple of questions left from Laurent and Laura. I'll note them down. If we have time at the end, we can come back to them, and or we'll send you an email with the answer. But I'll take note of that. Okay. So yeah, let's take a break now and see you at 11.
Okay, see everyone at 11 o'clock, and we will then have presentations from each of the projects that were successful in the first round. Everyone will be given a presentation, and we'll demonstrate how this WeldGalaxy project has helped them with the successful development of their innovation. So thank you. See you all again in just under 10 minutes. Okay, thanks. Paul, would you like to? I'm still sharing my screen, I think, at the moment.
Yeah, you are indeed.
Okay.
Geoff, you'll be making a short intro, I believe, 5 minutes, from 11 o'clock.
Yeah, I guess you could leave my screen up, couldn't you? Actually, yeah.
So yeah, you can just leave
it. Okay. Yeah, leave it there, and in fact, I'll put the next slide up. There we go. Yep. Okay.
Okay, cool.
And I'll give a short intro, and then I'll hand over to you to give presentation rights to each of the speakers.
Yes, I'll take care of that. Cool.
Thank you. See you in a few minutes. Thank you. Oh, difficult. It's finishing.
No.
Okay, welcome back, everyone. Just check, Paul, you can hear me?
I can hear you. Yep, no problem at all.
Okay. Shall we make a start?
We can indeed. Go ahead. Sure.
Okay, thank you. I can't see who's on, so I'm just assuming there's still an audience there. So I will now launch the second, or indeed the third part of today's webinar, and we've talked about the call that is the current call. We'd now like to go back and celebrate the success of the 10 projects that were chosen in the first call. So those projects are nearly finished. They finish at the end of the month. So we're just going through that formal sign-off process. And I would like to basically introduce you to those 10 projects, which I have up on the screen at the moment, and give them an opportunity to make a short presentation about each of their projects and to demonstrate how they've used the WeldGalaxy program to develop their innovations. You'll see we have a number of projects here, quite a wide range of topics, from robotics through to weld monitoring. There's one project on digital twin of a robot welding system, projects involving artificial intelligence, projects on additive manufacture using an Ark process, and also one project which is particularly focused on the environmental and the health and safety aspects of welding. So each of the projects will be presented by the representative from those projects. Each one of you has 10 minutes in total. So we're looking for around about 6 or 7 minutes for you to make a presentation, and a couple, 2 or 3 minutes at the end for any questions. So we'll take questions after each particular project. And I would just like to ask you, please, if you can keep to the time to make this event run smoothly. So at this point, without further ado, I'll hand over to Paul, and Paul will invite each of you to make your presentation in the order that we have up on the screen there. So over to you, Paul.
Yes, so I think the first one would be Dominic, and Dominic, you can now present.
So I can see, you can see my Outlook calendar right now, but that's going to change soon. Here we go.
Yes, we can hear you. We can see the screen too.
All right, let's see if I can even get my camera working. That would be great as well. All right, here I am. Yep. Hi, everyone. My name is Dominic Nestler. I'm here today presenting for Centen. Let's go back here. And yeah, our pilot was called Weld RDR. So it's basically an automatic and AI-based software solution to detect weld defects on X-ray images. And I want to take you on a quick tour through the program. I'm going to start off with a short flashback on the start where we initially began, our initial action plan that we laid out, and then take you through the actions we did in the last 6 months. And then talk a little bit about the support we got from TWI and FundingBox, and top that off with a short video touring around the pilot, showing some features of the software. So this was our initial working plan we laid out together with our mentor Vinod and George, and we basically had 5 milestones or 5 working packages we wanted to cover, with some requirements engineering, model training for the AI part, and software development, so integrate the model, bring it into the cloud to make it scalable and usable worldwide, and then conduct some user studies to, yeah, just trying to make an intuitive, good to use software for the daily and everyday use to make the change from current software systems easier, and then some business development during the business mentoring. So what did we achieve? Basically, we got everything done in time. We only had one smaller issue or matter we're still working on, and this is the model training. And in a few slides, I'm going to talk about what we found out during the program, and with the support of TWI especially, and their expert knowledge, as Geoff already mentioned, which was really great throughout the whole program. And I'm going to focus on a few things in particular to just give a broad overview on what we did and how we evolved during the project. I'm going to talk about the features of the software, which was really important for us right from the beginning. Then the labeling of the defects or indications on the images, and then NDT standards and user experience study are the main topics I want to focus on today, and yeah, give you a brief overview in just 6 minutes. So we first started off, or basically right from the bat, we learned so much during the program just by talking to our mentors at TWI. So before the program, we already had a software in place which was able to view and examine X-ray files like a TIFF or DICONDI format. But we quickly found out that we were missing crucial features like the line profiling you can see on the top right, and also a scaling function you can see on the down the right, which are mandatory for even doing a proper evaluation. And those features were not included in our software when we started off. So that was the first learning we got, and the first thing that we actually did is building those features to move forward in the project. The second thing we also found out very from the beginning in the discussions with the experts from TWI is that the image data set that we brought into the project was about 7,000 images. And the labeling of the defects or the imperfections in the images were not sufficient enough for an AI training in regards of what the actual jobs looks like. So the problem here is that the indications or imperfections are all labeled with bounding boxes. So the problem here is that there is too much of a margin between the actual imperfection and the indication by the label. So this makes it yeah, not possible to measure and to later on verify according to standards and regulation. So we had to adjust that, and we had 7,000 images, as I mentioned. So that was a hell of a lot of work. So we had to hire a freelancer there to change the labeling. So on the left-hand side, you can see what it looked like before. and to what we had to change it. So you can see that there's much more detail on each of the imperfections. There's no margin, and we changed the way we label the defects from bounding boxes to polygons. That was very crucial and took a lot of time. That is why we still in the progress of training an AI model. We already have a first initial model, but it needs some updates on performance. So we do not cover all flaw types yet with the automatic analysis, but we do have great success on first flaw types. So we need keep going on that to get the AI performance up. Then I want to talk real quick about the user experience study that we did. That was very helpful. Again, working together with TWI, providing us just expert knowledge. We focused on main two things, functionality and design, to basically find out if the software was built right, and if there are any missing or broken features, if it is intuitive to use, or are there features that are need a lot of explaining in order for the participant of the study to perform certain tasks. And also here we got really great results that led to really fast improvements. For one example, up on this slide, where it showed in the study that the users attempt to create a new project without entering a file name for it. So we changed it and put there a new label to make it more clear on how to create a new project. And those are just small things we could change really quickly through or with the help of TWI and with the help of the whole program, which we got achieved really, really fast then. And then last but not least, one of the major milestones was the integration of NDT standards. So we decided to take the ISO 5817 as one of the most common standards, and then integrated the ISO 10675-1 for steel, nickel, titanium, and their alloys. Or all acceptance levels are covered. And basically what it does, I'm going to show that later on in the short video I prepared. It gives you the possibility to validate the highlighted or shown imperfections that were detected by the algorithm, to validate them according to the standard. And this is a big step to bringing it actually into production or out of a pilot phase, because you can actually validate your results and see if a weld is acceptable or not. So that was it about the progress we did and all the great things we achieved during the program, and with the help of TWI and FundingBox. I want to mention and focus on that real quick here. As Geoff already mentioned, expert knowledge right at your hand. We got great software feedback. We got a way better understanding of what the customer needs by talking to the experts. We could improve our features, as I just showed. We got a great consulting on the NDT standards, which made it possible for us to select the right standards and get it in place. Provided us support for the user testing, and it was just so valuable to us because we're a software company, so we have software developers, mechanical engineers, but no real background in NDT. So that was really, really helpful for us to get this going. And then FundingBox just had a great network. I mean, basically the business mentoring was helpful for most of us, for the most pilots, and they just connected us with the right people. So our mentor, Matteo, he has a PhD in materials engineering, so he knows what he's talking about. He's an entrepreneur himself, which is for us as a small or basically a scalable startup is really important. He's an expert in funding NVC, was part of UC Berkeley training, top 500 innovators, and that all was just really helpful. They just brought us together with the right people so that he could help us with the topic on the business side where our concerns lay at the moment, and this is getting funding and investment. So that was just really helpful altogether to get to know those people, work with those people and experts in their fields. And that was it about the presentation. And now I'm going to switch real quick to the short video, and I hope I'm not exceeding the 6 minutes by too much. And then I'm happy to take some questions if there are any. So I'm just going to hit play and talk a little bit while it's showing. So what you'll see right now is some of the features I just told you about. This is the line profiling, where you can see the gray value distribution in a certain area. And then we have the color stress or contrast stretching, where you can optimize the view, examining the X-ray files for a certain window or box. On top of that, you get some image statistics on the images, and then we go into the next image and we hit the evaluate button, and this is where the AI starts evaluating the weld seam. And right here we found some porosities, and we do it on the next image as well. The computing time, by the way, is around 2 seconds on a GPU. And what we have here are detections of welds. So we have a weld detection. I'm going to pause here real quick. Why do we have a weld detection? It tells us whether the weld is horizontal or vertical. This is really important when it comes to validation, to get heights and lengths and width right. And then what we can see here also is that we have an indication of the probability, although this percentage is not an absolute value, that the algorithm is 77.5% certain that it is a porosity. It is or needs to be understood as a relative or relatively. So in this area, which is marked there, 77.5% of those pixels, so each and every pixel is classified, are classified as porous, and that is where this result comes from. And then once again, this is the line profiling, where you can see the gray value distribution, and this is where we can validate or shown how to validate the found flaws according to NDT standards. So you can see that we had checked or changed the standard to level 1, and before that we passed the test. Now we reset it and revalidate it, and now we failed, and now we even get the indication while it failed, why the weld seam is not acceptable, and we get an indication here. Now we have another example for that. Here we have a copper inclusion, and then you get the get shown that the copper inclusion is not permitted, and you also get the information about the undercut that is too large according to the standard, so it's not acceptable. And this is basically a very, very quick glimpse of the software. It continues for a couple of more minutes, but basically shows more examples of the automatic acceptance check according to the integrated standard. So that's it from my side. I hope it wasn't too fast of a walkthrough. I really wanted to show you as much as possible in those 6 to 7 minutes. Thank you very much, and thanks again to George, Isabella, the whole team. It was great being part of the whole program. Really learned a lot. It was really helpful moving us forward, moving the product forward, moving the weld area forward. Thanks.
Thank you, Dominic. Thank you so much. All right, Geoff, apologies here. I actually started reading the list from the bottom. Dominic was actually planned to be in the last pilot. So now we can move on to the actually first pilot that was supposed to present. That would be you, Christian, if I'm not mistaken. So I'm going to make you.
Paul, I didn't want to say anything, but I did get a little bit confused then. But thanks, Dominic. That was a great presentation.
Thanks.
Okay, you can go ahead, Christian.
Okay. Have you prepared some slides to show, or do I share mine? Just to.
You can share. You can share.
Okay. All right. Let's see. Do you now see something? Presentation?
Yes.
All right. Great. Thank you. So yes, this is Christian from Cavita, and our project has been the WeldCam. And in the project, we received a funding of 100,000 euros. We got to test our camera at TWI, and we also received the mentoring from the FundingBox, which was very, very helpful for us. So a bit about the background. So a challenge in welding is typically how to see. So welders use masks. But if it comes to cameras, then you're limited to certain things. On the left side, you see a normal view. On the right side, some versions where the camera uses filters like non-entity filters, or high dynamic range cameras is another method, which are basically based on the process light, and you don't really see a lot of details. And Kavita has been over the years an expert in high-speed laser illumination that is used in welding. And the idea is that you can see, get a bit more clear image of the welding. So with the help of active laser illumination. And market is mainly for semi-automated welding and also fully automated welding. And at the moment, it provides a live view of the process. And so basically, it's based on a bandpass filter, which filters out most of the process light. And then we have short laser pulses and a short exposure time, which basically reduces the process light to a minimum, but still gives a nice view to the process and full illumination. That's the background of the technology. So in the WeldGalaxy, we had a couple of goals. We wanted to map the welding processes and also what kind of defects we could see with the camera. And then we also had goals for the product development, improving the product as such, and to optimize for certain situations, and also synchronizing process data with video data. And one aspect was also to get higher frame rates for troubleshooting. Those were the main goals for the project. And now we'll go more into the stages that we had. So in the stage 1, that was like 2 months, end of last year. So we optimized the camera. So the hardware to improve the cooling of the camera. We also started development of this Ark sync. So the idea is that you take a picture, you match a picture to a certain part of the process. So you can actually freeze a certain stage of the process, which get also realized as a quite nice view to the process and a stable one, also for analytics important. We started the development of our camera with 500 frames, and then also starting evaluation of options like cabling, cooling, and also data acquisition systems. So after step 1, so we had like improvements, and that when TWI came in, so we sent the camera and they tested the camera and checked it how's the usability and also what kind of things we could see. And overall setup was quite nice. Only the arms, the mounting arms that we provided were not so rigid, but at least they found another option to mount those. And also there were some improvements for the recording to make it a bit more intuitive, that we got feedback for that. Video quality was overall very good, and I will show you some examples. So here's like a tick cladding. So one could see the melt pool in the edges. So one can also consider that for automation at some point to check the position. Here is an example of CMT. There the melt pool was not so clear anymore to see, but it's something one can check. One could look into later on. Here is an example of MUG welding. So on the left side, one can see spatter, and on the right side, one can see the orientation of the wire to the wall, and that can also be good for automation later on. So then stage 2 started in the beginning of the year. That's when we finalized our camera to get to 500 frames per second. The original model was up to 60 frames per second. We tested robot cables and also had some connectors to bend 90 degrees. That has been also something of interest in tight spots. We finalized the sync unit. We also made a mirror holder for 90-degree viewing. So for example, if you have inside pipe welding, that you can put it in there. We also tested a vortex pipe for air cooling, because in some conditions the camera might need cooling, either active water or air. And also we had some different mounting options. We also had some software improvements, let's say triggering the recording from an external event. We tested some data acquisition systems, but the one we chose initially didn't work. So that would need more customization to get it work from the supplier, and that was not possible anymore in the frame of the project. And we also tested some AR goggles, how that would work with our camera, but the ones we tested were not really fit for industrial use. All the improvements in stage 2 we were not able to test live because the system is still stuck in customs. So it was sent end of February. Let's see when it comes. Yeah, that was it.
Okay, thank you, Christian. Well, for now, no questions. So I guess we can actually move on. Yep.
Paul, I would just like to make a comment before we move on. Yeah, Christian, it was unfortunate your camera's stuck in the customs, but I just want to reassure everyone that we still hope and plan to do the testing once it arrives at TWI. You know, it's difficult times at the moment in more ways than one, but we want to make sure that we fulfill our role in the project, and we will do those tests as and when we get the camera. So thank you.
Okay. Thank you, Geoff. Thank you. And also thank you for TWI and the FundingBox team for this project.
Thank you.
Thank you,
Okay,
Christian.
Paul?
Yep. Okay. Well, we can then move on to Laurent. Laurent, I'm giving you the presenting rights right now. And there you go.
Okay. Show my screen. I think it's this one. Can you see my screen, Paul?
Yes, indeed. Yep.
Okay, perfect. Thank you very much. So my name is Laurent Marquis. I am from the FlexX company in Denmark, and together with Robotics, we have run a project with WeldGalaxy Support, what we call the intelligent welding cell. And the whole idea is to use the robot as a main workers in the cell to program itself, to configure itself and make the welding. So our idea for the WeldGalaxy, it was to develop a pilot solution that we install and test by FlexX and Robotics as a test facilities. At the beginning, it should have been at TWI, of course, and then we had this issue with the situation we all know, so we have to find other solution. And the whole idea to show, of course, how the cell is working in an intelligent way. And next step is, of course, to verify the cell and be sure that the items we can put on the cell can be validated and show the ability of the cell to change the configuration very quickly and make the welding also by the robot on complicated items. Oh, sorry. Oh. Okay, so implementation phase. So we have two different phases in the project. Of course, the whole requirement specification of the experiments, and after that we make the experiment, started to prepare the experiment. That means the design of the different components. Also makes the weld assessment we want to do on the cell, and this is been done together with TWI, and also we had to involve the Danish Technological Institute in Denmark to do so. So that's a RTO in Denmark we have in the project. And there's the last phase, which is a complete installation of the experimental setup, where we produce a component, we install the thing on the site. We had also to make an agreement with Yaskava to get a robot for testing the cell. We also have to involve a welder component inside, and we choose Kempi from Finland to loan us some equipment to make the test. And DTI prepares a digital twin of the whole equipment, and we make the setup. And now we are just waiting for making I will say the last phase, which is making the welding on the cell. You will see in some moment how it's work. Oh, I have really problem with the mouse. Yes, here. So here it is experimental setup. So the whole cell you see here, which is developed and made by FlexX, a robot from Yaskava, the Kempi system we have, and then we have to put everything together with all the components, the frames, the hexapod, the different grippers on the top of the hexapod. You can see the whole phase. with a project. I just start from January, because before it was the whole design of the cells, and we receive the export in January. We make the frame in January. We have to build everything together. We get the Yaskawa robot in the end of January, but we could put it on the cell before the end of February, when we receive the frame and things like that. So we have some issue, I will say, with the situation we have in Europe today with the corona. So things have been quite difficult to deliver. But we succeed to make the programming of the cell and make the first setup. And as I said before, the only thing we have all the equipment for Campy for making the welding, but it is going to be installed right now for this. So here you can see the whole cell built with the hexapod, with the robots. We have made some setup of that. We have the robot program working for that as a whole cell. We have this digital twin from DTI working, so we know exactly the position of the hexapod. We have made 3 different setup for the cell to test the ability of the cell to change from one configuration to the other configuration, and then it's working quite well. So here I will show you hopefully a video. Yes, can you see it without problem?
Yeah, it works perfectly.
Good. Perfect. So here you can see the robot is configuring the cell. We have already put the element to be welded on the cell, and here it is adjusting. And for instance, this is a first setup where we have verified, of course, the distance where it puts the element, and the idea is that the robot is going to make the welding after that. The robot is positioning the cell in home position, in 0 position again. And then ready to configure the next setup. So adjusting the fixture again, placing the part in position for welding. And here you can see we have changed the distance to the edge, and we have also rotating in different way the element to be placed. This last setup we test. So again, a different setup, a different geometry, a different angle of the part. And the whole idea is, of course, after that the robot is taking the welding head and make the welding on the cell. So very interesting project, I will say. We succeed to do as much as we could during the 6 months, which is always, of course, very pressing in time. So now we are just installing for making the welding on the part. So from the support we get from TWI and FundingBox, I will see that our mentor, I want to name it, Lei, was a very good help. We had a meeting every 2 weeks together where we evaluate the technology, have some technical discussion together. We define together the welding assessment, and Lei, of course, help us to validate the report and all the support thing we have done. From the FundingBox area, so I think about this marketplace, I will show you, and the business development, we have, I think, quite a good, interesting discussion, of course, on the WeldGalaxy platform. When we implement our products, the legal entities, we are starting to make some knowledge page. We are starting to make some blogs also inside the system, so it's working quite well. And on the business development, we have built also all the canvas business activities, all the different blocks that we need for that, and it's working quite well. We have a good support for that. So I will say that's the whole I want to tell on the project. And again, thank you very much for the whole team from WeldGalaxy and Lei, because that was a great support, and it's helped us to move quite a lot with our project and get some very good result on that. Thank you very much.
Thank you, Laurent. We actually have a question from Lei, so if you don't mind staying with us a little bit more. So, hi Laurent, very nice work and presentation, thank you. A question, if you don't mind.
Absolutely.
Yasakawa robot was used in your project and demonstration. could the flex hex fixturing be also integrated with other robot makes? Do you have to do a lot of bespoke integration work to change to a different robot make?
Yeah, very good question, because what we do, because we have this agreement with Yaskava, they loan us the robot, but in principle, we are using the RobotDK platform. So it's quite easy to integrate another robot inside. Of course, we have to make some programming inside, but it's an open platform, you know, so it's not a big difficulty to do that.
All
The
right.
thing is that the robot has to be in the list of the RobotDK, but most of the robots are inside. Yeah.
Okay. Okay. Thank you, Laurent. Geoff, any word on your side?
Sorry, I had my microphone off. Yeah, very interesting. Thanks very much for a good presentation. And yeah, we look forward to seeing the final welding results. I think in a week or two. So thanks.
Welcome. It was a pleasure.
Okay, well then, Laurent, thank you so much. And we can now move on to, so correct me if my pronunciation is wrong, Gel. You can go ahead. I'm gonna give you the presentation right now. There you go.
Okay. Yeah, you were almost right. It's Jelle.
Okay.
Let's see. Let's see if I can find my presentation. Can you see the screen?
Yes, we can. Yep.
Okay. Okay. So my name is Jelle van Kleef. I'm a CTO at MXUD, and I will give a short wrap up of our WeldGalaxy project called Duku. We've done it with the help of the Belgian Welding Institute and, of course, our TWI mentor, Adrian Edison. At MXUD, we do a lot of wire and arc additive manufacturing. So we print lots of parts. And the recurring task is the search for the correct welding parameters with the desired properties. And an important property is the bead shape, so especially the width and the height. And in the case of shell printing, this corresponds to the wall thickness. So, well, once the welding parameters are found, a second step is the measurement of the layer height, and we need that to generate the toolpath for our additively manufactured part. So all this can be quite time-consuming and requires much manual labor. So automating this process has been our WeldGalaxy proposal. I see there's a mistake in the bottom there. So our idea was to print a number of walls, each with their own parameter set, and to measure the resulting properties, all automated. So the two most important factors for controlling the weld are the travel speed and the wire feed speed. So we decided to focus first on these two, but with our solutions, it should be trivial to vary other parameters as well. So since the inter-pass temperature is an important aspect as well, to have reproducible weld shapes, and WAM parts tend to get pretty hot, we included the pyrometer as well. So in the lower right picture, you can see the setup that we've come up with some printed parts, plastic printed parts to mount everything. It's an experimental setup. So it consists of the pyrometer and the profile scanner to scan the walls. And in the upper right picture, you can see the industrial PC that we have chosen. So a procedure has been developed that takes a configuration file that defines how the experiment should run. So the parameters to be varied, the ranges, the step sizes, as well as the number of layers to be printed, the desired interpass temperature, and so on. So the desired welding parameters are communicated from the industrial PC to the robot, which in turn controls the welding machine on the fly and sets the desired wire feed speed, for example. Then the operator points the robot to the starting position on the substrate, and the process runs automatically. It starts with a scan of the substrate, then the robot prints the first layer of the first wall, and then it's scanned again. The results are saved, and the toolpath of the next layer is calculated automatically, and the next layer is printed. So you can see a time lapse of that in the right side, and you can see we try to minimize the warping of the substrate, so we alternate the position on the beam. On the left side, you can see that the robot is doing a scan, and it's zoomed in on the upper right side. You can see a projection of the laser blade to scan the wall. So here you can see a typical result of a scanning of a complete wall per layer. So the blue lines are the wall width, and the red lines are the wall height. And you can clearly see that the first couple of layers, the layer width is less because it's printed closer to the substrate, and the cooling is much quicker, the solidification. On the right side, you can see the beams of all the walls we've printed on the beams. One is missing because we cut it off. So in total, we printed 35 walls. We did experiment on carbon steel and stainless steel. Yeah, so this picture is a carbon steel graph. So when we aggregate all the data of for example, the carbon steel, and we come up with these pictures. So what we can see here is that we varied the travel speed, and we did the experiment for 2 distinct wire feed speeds. And we repeated one of the processes to see the reproducibility. And as you can see, 2 lines are pretty matching closely. Yeah, so on the right hand side, we can also print the data in 3D, which you can see on the right hand side. So basically, it's actually a 4D problem: travel speed, wire feed speed, layer height, and layer width. So, but these are ways to represent the results. Yeah, so this is really going to help us out. We can quickly now find the desired layer width. And surprisingly, the wire feed speed didn't do much to the layer height, as you can see in this figure. Other than that, everything looks as expected. If you increase the travel speed, the layer width decreases, and also the layer height. Yeah, that's our WeldGalaxy project. Yeah, special thanks to our mentor Adrian. Yeah, it was a blast. We had a great fun doing this. So thank you.
Thank you, Jelle. Great to hear that. Well, no specific question regarding this presentation. Actually, we have one from Sohail. Thank you for the presentation, Jelle. What was the difference between steel and stainless steel data?
Well, it looked pretty much the same. So we put it in our proposal to do it at least for 2 different materials, but the trend in both of the materials was the same. One difference with stainless steel is that we did see a difference in layer height there. So with carbon steel, the layer height was pretty much the same for the 2 different wire feed speeds. With stainless steel, there was a small difference. But yeah, and of course there are some absolute differences, but the trends look similar.
All right. Okay. Thank you, Yella. So, well, I think we can then move on to the next presentation. And this one is being led by Max. Max, I've seen you already put your camera on, so I'm just going to give you presentation rights. And there you go.
I'm not sure which screen you are seeing right now. I didn't get
Go on.
Huh?
We can see your screen. We can see your screen.
With the presentation?
Yeah. Well, no, actually, no. Right now we can see your mailbox, Max.
My mailbox?
Yes, we can see your mailbox.
Okay. That's the wrong screen.
Indeed. Yeah.
So change screen. Here. Screen of monitor 2. Okay.
Yeah, we can see
That's
it.
better?
Yeah, we can see the presentation.
Okay, good. Yeah, well, thank you for having me, and thank you for the WeldGalaxy project. Basically, just a quick introduction what RebarTech is doing. We are working with rebar, so that's a concrete steel reinforcement, and we're working on a solution to automate the prefabrication of rebar cages. So here you can see a little bit of impression. On the left-hand side, you see a robot welding rebars together, and on the right-hand side, you see a robot placing rebars into a jig. Once you have done that, the next step is that you install the rebars on site. And if you look here on the left side, this is a mesh that we have made for a bridge project. And then on the right-hand side, you see something that is called a lap splice. So traditionally, the way you join different rebar cages or different rebars together on the construction site is an unwelded lap splice. And here the rule of thumb is that you use 50 times the diameter as a lap length. So that's a lot of steel, and it also makes the joining the cages on the site more difficult. So what we are doing is that we are in the WeldGalaxy project, we built a prototype for load-bearing welding of rebars on the construction site. I'd love to show you a few pictures of the prototype, but there's an NDA in the picture and there's patents, so that's why we chose to not show anything at the moment. But basically what we built during the 6 months is that we built several iterations of this prototype and also tested it together with TVI and a local lab here. So what you see on the left-hand side is a few samples that we have welded. And you see also they're bent a little bit. So that's because of the testing process and afterwards. And on the right-hand side, you see some auto tests that we have run with our solution, with our prototype. And the nice thing is, one of the main reasons to weld them is that you can reduce the lap lengths a lot to 10 times the diameter if they're welded properly. So yeah, then I told you about we bent them a little bit so that they fit in the machine. That's tensile tests we have run, and it's nice because they didn't fail in the weld. We've also tested the first version of our machine vision, where we basically, by a visual inspection, check the welds. It works quite okay, but our data set is basically way too small. That the data set that we have built in the test is very small. So we need to build a much bigger data set for that. Then we have together with TVI, we have looked into one of the big challenges here is that once you weld the rebars, a big concern of the customers is the fatigue properties that you change of this steel. So for example, if you're putting the rebars in bridges, they have dynamic swinging loads, and then the fatigue properties of the rebar are important. And here we got help from, it's an ongoing thing with the TWI right now, to basically make a literature review of what kind of existing research is already out there on the fatigue. Then we, together with Carlos, our business mentor, we did, and FundingBox, we did workshops on our business model. And we made these mirror boards. which I find to actually be a very interesting tool. I didn't know about this tool, so it's a nice collaborative tool for thinking out loud together visually. So I found that very helpful. But we have to also be honest, like we are in a very early stages with this prototype. So right now, our challenge is more of a technical nature than a business nature. But it was good to make these exercises on the business model. And that's all I have for you right now. Once again, thank you for having us in the project. We made a really good progress on this prototype, and we feel that this might turn into a nice product into the future.
Thank you, Max. Thanks a lot. All right. No questions so far. However, Jelle, if you're still with us, there's a question from Emil that I missed, and that I can ask you right now. Did you use laser triangulation for scanning?
Yeah, we bought a sensor that does exactly that.
Okay.
Thank you.
No worries.
All right. Okay. Well, then we can go to the next presentation, and that would be you, Nenad. I'm going to give you presentation rights right now. You have.
Okay. Can you okay? Okay. What can you see? Sorry.
Right now we can see your browser and.
Okay, but I would like to. Can you see now my presentation, PowerPoint? No.
Yes, we can. We can.
Okay, thank you. Okay. So hi, good morning. I'm Nenad Stojanovic, and what I'm presenting is our work in the WeldGalaxy. The name of the project is WeldTwin, which is very interesting. Us with all this, let's say, facility support.
Nenad,
yes.
I'm sorry to interrupt you. I personally lost you for I would say 20 seconds. Would you mind starting again? I think there might have been a short connection issue.
I missed it else, so I think the problem is that no.
Look, this is why I'm not sharing my camera, because I'm experiencing this morning, I don't know why, extremely issues with the connection. So I'm so sorry, really. So can you see the first slide, WeldTwin?
Yeah, we can see the first slide. We just lost the voice for a second.
And can you hear me properly now? Because once again, I'm so sorry. Can you hear me properly now?
Yeah, we can hear you properly. Yeah.
Okay, I will try. Okay, I will try not to do anything wrong here. Okay. Anyway, it's about introducing digital twins into the WeldGalaxy and actually in the welding process. And there is a extremely, I would say, interesting innovation regarding how you can introduce digital twins in order to support the monitoring and the quality of the weld. And usually, if you're talking about the digital twins, you have an issue in developing these things, because you have to model, or you have to do a lot of data-driven processing, naming analytics. And since we have a company which is doing this production of the twins out to the data in a very efficient way, this is exactly what we use here in order to produce in a very efficient way digital twins for the welding. And the last bullet point is extremely important, because TWI mentoring actually made this vision realistic. And I'm now going through the set of the slides which are really illustrating that what we are doing. So you have this welding. I just have to check. Can you hear me properly? And can you see my screen properly? Sorry for asking.
No problem. Right now, we can see your screen. There's just a welder, a picture of a welder on the left side.
Yeah, because there are now my presentation is full of animation, so I just wanted to check that everything is going smoothly. Thank you. So you have this welding, and what we are doing is actually, you see on the left hand and right hand side of this photo sensors, which are environmental sensors sensing the environment, air quality, temperature, and so on. And on the right-hand side, you see the camera, which is actually monitoring or recording the well. And what we are doing is, as you see, we are collecting all this data, recording the data, and what we are doing with the environmental sensors, we are recording all these sensors. So there are kind of 15 sensors, and you're getting batch of the numbers, which are actually reflecting what is going on regarding the environmental context during the welding. And now it's the place to say thanks to the TWI support, because that's what we're using here is a Caviter camera, thanks to Christian, who is also here in the teleconference, because actually when we started with Rob, who is our mentor, started discussing about cameras and so on, we had a list of the cameras, and then he made this connection with the Christian, and Christian was really extremely friendly and cooperative, and they sent us the camera, which is still in our places, and we are using this camera. So as a very practical evidence how we are really benefiting in a practical sense, let's say, from being part of this consortium. So once again, thanks to Rob, thanks to Christian, I really enjoyed in this context the cooperation. And now coming back to the presentation, so what we are actually doing, just imagine now collecting all these scenes, and that we are collecting all this data, and we would like to learn something out of this in order to simulate, let's say, the behavior of this welding process. And this is exactly the digital twin or twin. It's a digital replica of your asset, of your process. In this case, it's a welding process, and we are applying different type of the AIs. In this case, it's a deep learning, but a very specific one, because usually for the deep learning you need, let's say, hundreds of thousands of the photos in order to learn something. Since in this very case, because we are trying to learn some anomalies in the welding, the challenge was how you can learn anomalies, but by not having thousands of anomalous photos. And this is where we are applying some one-shot algorithms and other algorithms for accelerating deep learning in order to learn with, let's say, less data, high quality classification algorithms or classification methods. And this is the model which is then used for classifying. So in the real time, just imagine that you are applying again the camera, recording something, and the system is deciding. You can see with this red and green boxes if this is good or bad. Something which is very novel here is that we are using also statistical learning. So we have this on the bottom side, we have the sensor data, and from this sensor data, we are using statistical learning plus machine learning in the context of the data analytics in order to develop the models for detecting anomalies, multivariant anomalies in your in the data. So out of this part of the model is the algorithm, which is based on the readings from the sensors, deciding if in this very particular case there are some unusuality in the whatever temperature, smoke, CO2 or whatever, but in the multivariant context. So this is tricky since we are not comparing one parameter by one parameter, but we are taking all of them in a n-dimensional space. In this case, it's 15 dimensions, and then we are trying to develop this kind of the models. And this is our main artifact or goal or results. This is this weld twin. And I have a couple of slides more, and then I have a video, so I'm a little bit speeding up. The main idea here is that we are dividing real world and the digital world. From the real world, we are getting the signals, so you have the physical signal sensors. In digital world, we are interpreting these signals based on the models in order to detect, as you can see, some anomalies. So in the real world, we are catching things, and then in a digital world, we are transforming in a different way in order to do, in a very proactive detection of anomalies. Okay, this is another example. You can see here on the slides, so left or right, this multivariant case. So we are not considering parameter by parameter. We are taking, and this is statistical learning, taking all of them together in order to develop these models for anomalies. Our main result is actually this architecture. So it's a fog computing-based architecture that you have on the left side, something which is called extreme edge or edge. You have the camera sensors. Then in the facility, in the manufacturing, so you have this edge computer or industry computer, which is collecting all this data, then transferring to the cloud. And in the cloud, you have different type of the learnings, as I already mentioned, deep learning, statistical learning. And this slide also shows how we have developed based on the support to the 3 stages. First stage was dealing with the edge, second stage was dealing with the deep learning, and third stage was dealing with combining all of them in order to make a complete system. And this is the last slide, and then I have a movie. This is the last slide, then I would like again exactly to thanks to the TW and FundingBox by having a screenshot from our sessions related to the business modeling. Now I am talking to Isabella and the FundingBox people that it was an extremely great support for us, because we would like to develop the product out of this. You will see the presentation is completely promotional one. And this is one of the screenshots from one of the lessons. So we had the kind of 4 webinars, and then I had with my mentor, I had about 6-7 1-hour sessions with developing all this stuff related to the business modeling. So I would like to emphasize here is that from the point of view of business support, so if you would like really to make out of this the project, the support was really excellent. And this is one statement. I would like to read it. We developed with a mentor helping system for welding processes that detects anomalies and gives alarms, enabling optimized and ensure quality of the welding process, unlike other solutions that do not use environmental and energy standards. So also emphasizing some of the unique selling points. Now, now I hope you get. Can you see my browser?
Yep, we can see it.
Okay, now it's a 2-minute promotional video, so I hope that also the audio would be good. Can you hear it?
On my side, no sound.
No sound. Okay, this is a pity because there is a quite nice sound around it, but anyway. So obviously, because there is a audio coverage, but I'm explaining now how we are building the tree. So it's using data collection, and the data is collected, then there's a training process, and the tree is actually learning something out of the collected data. And solution is found, hasn't found. The solution is now applied. Solution is a model. Now in the real time, this thing is observing, alerting once the model has been, let's say, destroyed, and the thing is also code analysis. We can find out that these 15 parameters what was wrong actually. You see some of those. And these are technologies we are using. So first of all, digital twin in order to model the assets, then artificial intelligence for learning, and data analytics for applying this all in real time. And then from the data, we are learning the models. These models are then put in place for analytics, which are detecting then anomalies. They said it's pity that you don't get the audio coverage, but anyway. And we are claiming this is the quality, the future of the quality control, because you are really able to control your system in a very multivariant way. So taking into account all these, let's say, very specific elements which usually you are not covering, but by having them together in the weld twin, you can really make a universal solution. Sorry for probably going up and down, but anyway, I hope that you have understood, and I'm open for the questions. Thank you.
Thank you, Nenad. No, I think it was great. We understood everything. Just
okay, thank you.
But other than that, everything perfect. Okay, cool. Sorry for that. So now I'll be. Well, we actually have a question for you, Nenad, from Lei. Very nice presentation, Nenad. A quick question, if I may. Could those environment sensors get affected by arc welding processes, fume, flash, spatter, etc.?
Could you repeat? I couldn't understand the last part. Could these environmental sensors?
I can repeat that for you. Could those environment sensors get affected by arc welding processes, fume, flash, spatter, etc.
Yes, absolutely. So environment. Look, we are very flexible. No, thanks for the question, by the way. But when you talk about the twin, then the issue is that if you have an infrastructure for collecting the data, then you can collect whatever data you want. In this very case, our environmental sensors, there are 15 of. There was a device for environmental sensing which is catching 15 parameters. If we would like to extend to any other sensing, it is very easy just to add this kind of the sensors. So by really not knowing exactly what someone who is questioning is actually asking for, because I haven't answered this with a flash, but I'm just claiming that once we have the sensors which could catch that effect, let's say, it can be very easily put into our system, into statistical learning, in this multivariate analysis, and in the part of our anomaly detection model. If the person would like to have more details, I please share my email with him, her, because I would be really glad to answer in the details. Thanks.
Okay. Thank you, Nenad. That was question from Lei, that was one of the mentors. So I'm sure he'll ask you something if any details are required. And we also have Geoff, who has a comment here.
Yes, thanks, Paul. Nenad, very interesting presentation. I just wanted to highlight the fact that you actually worked, you collaborated with Kavitar. With Christian in this project, and particularly for those of you listening on, thinking about putting in new proposals for WeldGalaxy project. I thought it was very interesting that you were able to work together, and it's certainly something that we encourage, and I'm very pleased that you formed that relationship, and it was beneficial to both of you. So thank you.
I just want to emphasize, Rob, our mentor, was actually initiating this connection. So to be quite honest, this is the reality. He's a mentor of both of us, and he just made the connection. He was really clever enough in order to see that there is a synergy, and then we communicate with the Christian now, thanks to Christian, several times, and so on and so on. So actually, excellent environment for collaborative work. Thanks.
Great, thank you, Nenad, and thanks, Rob.
Okay, thank you, Nenad. Thank you, Joe. Then Pedro, you're the next in the line. I'm gonna make you a presenter right
now. Okay, hello. Can you? I don't know. Can you see my screen and hear my voice?
We can see your screen, hear your voice, and even see you.
Perfect. Okay, so we good to go? Okay, so again, hello everyone. I'm representing Sarkis. We are a company in Portugal that we are focused on robotics. Essentially, we develop software solutions for welding and cutting systems, and then we integrate it on robotic systems. So in WeldGalaxy, our pilot trilogy is focused on 3 areas: robotics, welding, and knowledge. And this is achieved by stages. So the first one is the study of the process itself, that is welding. And this led to us defining a taxonomy for welding quality. This was the part in which we got most help by TWI and from our mentor, Wei, because, well, this is the crucial part of the process where we define the important parameters and the important outputs that we need to get from the welds. Then, of course, you need to integrate this knowledge get from welding and from welding process in the robotic system itself. And now I would like you to imagine having a robot, but with eyes and a brain. And you not only would have a perfect machine, but you would also have a highly efficient operator. And that is our focus. So we integrate the sensors to detect the welding joints and also to review the welds once they were concluded. And then we integrated the machine learning system solution so that we can actually find what is the correct parameters for the structural steel industry.
We applied this to two sectors. The first one was the production of pipelines, and then the second one was the structural steel area, where we did 3 trials on winner welding, boxings, and also multi-layer welding. And yeah, everything was done built on top of our software, the Metroid ID family, where we generate automatically welding vectors, and then we can improve on top of those welding vectors using the data that we got from the project. So just to sum up the main goals from Sarkis software, we have 4 points. The first one is the automatic visual detection of the 3D device and translation to robotic motion, and that is mainly the sensing. Then we have the automatic repositioning for high redundancy robotic systems, and this is definition of the posture for the robot in this step. And then we have also a software that is a way where we can make the robot the full extent of the human operator, and where we can actually provide the user the correct information on what's going to happen and how it's going to happen in the real work cell. And then at last, the process and the motion generation is the output of the pilot and also of the software itself. So just a small preview on the software. Our software is essentially a offline programming software solution where we generate welding vectors from the joints of the parts that need to be welded. And then we correct the vectors to avoid collisions and to avoid access to the parts and to the welds itself. Once we do that, we correct the vectors and we add the robot on top of that. We translate everything to robot code, and we can perform the weld or the process that is associated to the robot. In this case, it's always going to be a weld. For the trilogy itself, the machine learning was one of the main outputs of our solution. Here we tried some. We verified that the best one was using random forests. And essentially how this works is we have welding parameters that we have defined on our taxonomy, and we have the measure results. These are typically the volumes. We use a laser line to detect the volumes, and also the visual aspect of the weld, and also some stress test on the weld because the weld needs to be resistant. And those were the main outputs. And using those and combining those in the random forest algorithm, we were able to define a classification model. And then we applied the prediction stage. That is the second stage. We had the classification to well detect if the weld is good or not using some parameters. And then we have the second stage that is getting the right parameters from the classification model that we have created, and also for the measure results that we have and we wanted to have. So in this case, we use Monte Carlo, and the results are let's say resumed in these tables. We did multiple testing, but these tests are just for the classification and the prediction part of the system. We have good accuracy rates, and the most important let's say contribution of the project is that we ensure that the quality of the weld is good, and we also increase the uptime of the work cell. And yeah, essentially, we want to thank once again to the TWI, because all the technical development was led by us, but TWI has collaborated a lot. In particular way, I would like to identify him once again, and also to the FundingBox, because they help us putting this technological idea and put it on a business standpoint. So that was my presentation. I'm then open for questions.
Thank you, Pedro. Thank you. Thanks a lot. Okay, we have one from Lei. So hi, Pedro. Thank you for the nice talk. It was nice working with you. May I ask you a question, please? MAG welding process for fillet welds was demonstrated in your nice work. do you have any plan to further develop the machine learning for other welding processes and weld joint types? For example, TIG welding for butt joints used by high-value manufacturing such as aerospace, nuclear, etc.
Yeah. Thanks for the question, Wei. Once again, it was a pleasure to work with you as well. But yes, the concept behind this project was, in fact, for MIG-MAG welding, but this can be applicable to other welds. The prototype itself, it's let's say a flow of information, and that flow of information can be dealt in multiple areas. So we are not going to restrict the software to MIG-MAG. In this case, for linear welds or pipelines, we can expand this to TIG and for the automotive and also to the aerospace industry. So in answer to your question, the software is open enough and flexible enough to be extended to other areas. Yeah.
Okay. Thanks, Pedro. Well, no additional question. Leia's thanking you. So thanks again, and we can move on then with Rodrigo. Rodrigo, I'm gonna give you the rights right now. There. Hi, Rodrigo.
Hello. Okay. Can you see my screen now?
Yep, we can see it.
You can see the presentation? Yeah.
Yep.
Okay. Thank you very much. So my name is Rodrigo Linares. I'm the business development manager of the company New Infrared Technologies. We are a Spanish company, and we were involved in the pilot called Ark. Okay, yeah. Just a brief overview of the pilot. This is similar to the presentation that we did, what we showed in the kickoff of the project. So the main goal of Ark is to build a closed loop feedback control system to control the voltage of the arc welding of the arc using an infrared camera that is measuring the melt pool width and calculating the optimum voltage. This is what I'm showing in the diagram on the right. So we have the camera that is looking at the process area. Then this image is being analyzed. We obtain a measurement of the melt pool width, and then with that we can calculate the optimum voltage and drive the voltage control in the polysode torch. And with this, the aim is to improve the quality of the whole process. So, and just as a summary, in the stage 2, we had several objectives for the project. So, first, we wanted to study what would be the configuration of the equipment that we would use during the TIG welding process. In order to define how the camera would be integrated and actually what electrical signals were needed to control the process in real time. Then we designed it and performed a data collection experiment in order to study the effect of the voltage variation in the melt pool as it's measured by the infrared camera. And this would help us to obtain a correlation between these two parameters so that we can build a performance model that we can implement for the closed loop feedback control. In the image, you can see the equipment that we use for this experimental phase in the stage 2. We have the infrared camera, that's the orange box that you can see on the left of the torch. It's a camera that it's an uncooled camera operating at 1 kilohertz with detection in between 1 and 5 microns. Then the data, all the images are transferred to the PC, and which we will analyze later using our software. This camera is built, manufactured by us. And then we have the TIG welding system, which is made from polysode, and it has an automatic voltage control system that we intend to put our closed loop, to integrate our closed loop control. For the experimental phase, we designed 4 experiments. The first one was aimed to obtain data samples from processes that are required at constant voltage. So we defined several steps, several voltages. We were increasing this from 10.5 up to 17 volts in steps of 0.5. With this experiment, we want to study the variation of the melt pool width measured with our camera when the process voltage changes. These are the curves that you can see on the right. You can see in the upper here. You can see how the melt pool width is varying, is changing as we are increasing the voltage of the arc. And this, the results of this experiment let us build this correlation that I mentioned in the slide before, which has in which we can see the variation of the melt pool width as we change the R voltage. Here you can see that we have like a quite linear response, which is get up to 14 volts. This will be the model that we will implement for the closed loop feedback control of the voltage. Then we have made a second experiment in which we have used a sample in which there are 2 copper heat sinks on the sides, so that we can see what is the effect of the melt pool width as the process is passing next to these areas where there is a larger dissipation of heat. So this is the result of this experiment. With the camera, we can see that the melt pool width is being reduced as we pass next to these copper heat sinks areas. And here we can see if we binarise the image of the melt pool width with the time. With the time here, we can see how the melt pool is stretching as there is larger diffusion area. We will use this experiment also to validate the operation of the feedback control system. We made then other experiments that helped to build the model that I showed in the slide before. So then with these results, we went to the stage 3, in which we had 2 main objectives, which were to build a prototype system that can be installed in the test bench and be introduced into the automatic voltage control system. And then, of course, perform a data collection experiment to demonstrate the feedback control loop. In the photo, you can see the installation of the prototype. Now we have in the camera, we have the infrared camera, the image processing electronics, and the control electronics, everything embedded in the same camera. And this is the system that will look at the process area. In this case, you can see the sample with the 2 copper heat sinks, and will perform the closed loop control of the arc voltage. The idea is to keep the melt pool width constant during the complete process, which will increase the quality of the process. The experiments that we did, once that we have integrated the camera, and we were sure that the closed loop control of the voltage was working, we made a couple of experiments just to demonstrate the feedback control loop. In this case, we used the samples again with the 2 side heat sinks because we want to see if the camera is capable to control the melt pool width in these areas. And we also used a wedge sample, which is reduced, which is increasing the area, and this has, of course, the area of diffusion, and it has an effect in the melt pool width. Just to simplify, I'm going to show you the results of the experiment TT and T4, which are shown in this slide. So these are the curves that we obtained with the camera as it's working during the arc welding process. Here we have on top T3, which is a process that is done with constant voltage. You can see it's done with 13 volts. You can see the red line when there is no control. The red line represents the melt pool width, and you can see how the melt pool width is changing, starting here, and it's changing. It gets up to 10 millimeters more or less, and then it's reduced when the torch passes next to the heatsink areas. This is the behavior that we have seen in the stage 2, so it fulfills the experimental results of the previous phase. And then we can see in this area where there is no heatsink that the melt pool starts to grow again. It goes around 12 millimeters, and then when the process passes next to the second heatsink, it's again the melt pool again is reduced, and then it goes up again. So this matches the experimental results that we have found in the stage 2. However, if we introduce the voltage control and the closed loop control system for the Ark voltage, we can see that here in the area where the first heatsink starts, the melt pool goes into around the initial value here, which is around the 9.5 millimeters. And then we can see that during the whole rest of the process, the melt pool is quite constant. And when we get to the second heatsink, it goes down a little bit again, but not as much as it was in the non-controlled process. And then the melt pool remains again around the initial value. Here we can see more clear with the photos of the two processes. Here we can see that there is an area here with where it seems to have a lot of arc intensity, but clear you can see that the melt pool is increasing in these areas when there is no control after the two heat sinks, whereas in the control process the heat sink remains constant. This leads to a better stability of the melt pool width, which has been achieved with the voltage control. So just to summarize, in this harmony, in the experiments for the harmony, we have demonstrated that there is a direct correlation of the applied voltage to the Ark and the measured melt pool width with the camera that we are using. And we have developed also a prototype that has been installed in the test bench, and this allows to monitor the melt pool area during the weld process, calculate the melt pool width, and make a control of the Ark voltage during the welding process. And this leads to a better quality of the process. And this is a quick summary of the project. I would like to say to give a special thanks to Adrian, which was our mentor, to Liam and Alex at TWI, which were helping us with the experimental phase, and then also to Emilio Sola, which was our mentor for the Canvas, and the FundingBox team, and Espen. So thank you very much. And with this, I reached the end of my presentation.
Thank you. Thank you, Rodrigo. Okay. Well, no questions so far, so we can actually get to the next presentation. Thanks again, Rodrigo and Emil. Hi. I'm gonna give you the rights.
Very good. Thank you.
Yep, you have them.
So. See. Can you see my screen?
Yep, we can see it.
Very good. Yeah, so also welcome to the crawl pilot, a new concept for a clean and safe cobalt welding cell using intelligent sensor and data management that we realized in the last 6 months. What was our motivation? Our motivation, if you imagine you are the owner of a small welding workshop and you have several problems. You have problems to find qualified staff. If you have nice orders, you still have productivity pressure. You may have concerns from your welders that welding is not safe, it's not a clean process. And you have the challenge to show your welders and also your customers, I'm able to produce high quality parts and still having a safe operation. So this was our motivation to create an easy to automate welding solution due to missing welders to meet the increasing demands in health and safety and environments for operators and also bystanders, and the need to record and process data for documentation. And finally, this has to be achievable for small and medium-sized companies who have limited investment opportunities. So that was the starting of the crawl concept, this intelligent and safe robotic cells to address the staffing situation. Yes, we said, okay, using a collaborative robot should be good for high productivity. These cobots need very few programming skills. You can learn to program that robot in less than 1 hour. And of course, the welder has no physical stress. You can also achieve all the customer requirements. A robot always has constant quality, high flexibility. And a cobot cell, it starts at around 40,000 euros, so that's a decent sum. And with our innovation, of course, we implemented monitoring of both live and recorded data, and we can evaluate consumption data. I will show you in a minute. You can see we applied fume extraction directly at the robotic welding source. That means more than 95% of all the welding fumes can be collected directly where they are generated. So how does such a cell look like? We built it up in our application center, and we granted live access to TWI so they can also witness and support us. The main components, of course, is the cobot, the collaborative robot, a welding power source, and in addition, we added a fume extraction system, a gas monitoring system, which allows us to save 50% of the shielding gas. We implemented also a power meter to collect the total energy uses and ambient monitoring for the created fume, and everything was built into a cabinet to, of course, have also the welders or the machine users protected from the arc. So in the next slide, I will show you 2 videos in parallel where you can see live welding and also the live recording of the data. The video runs for 1 minute, so I will have some time to explain. You will see on the left side what happens if you have the extraction, the fume extraction on, compared to a situation where you have the extraction off. Please observe or obey that we have a very small welding sample here, so the welding time is quite short, and you'll also see that in the data generation and especially in the fume values. What we display is and I start the video now. We display the electrical parameters of the welding process, so voltage and amperage, and also the gas flow and the wire usage. From these parameters, we can also collect and record the energy usage and the CO2 footprint. And on the 2 lower sensors, you can see the fume emission, and you can see that now the process has stopped. We still measure only very low fumes because the dust sensors are placed in a height of 1 meters and 80 centimeters where a normal user will stand. And you can see that now the fume reaches the sensors in the situation where the extraction is off. We end up at a value of maybe around maximum 600 micrograms per cubic meters, which is still below the legal limits. But of course, if you imagine that you would weld bigger parts or have longer weld time, of course, you would go over these limits. And on the left side of where the extraction was on, the maximum fume measured was always below 100 microgram, which is a factor of 10 below the limit. So this works very well. And afterwards, of course, we can look at the recorded data. So we have, when you look on the left part now, we have all data together in one diagram where we have the dust sensor data and also the welding data. So you can clearly see you first have the welding, and a little bit later the fume values go up. And you can also clearly differentiate, if you look on the left and the right picture, that the fume values, of course, with the extraction on, are significantly lower than without the extraction. So this clearly shows that we are able to realize a clean and safe welding cell, and we can really collect all the relevant data. So the final dashboard looks like this. So we have a user menu on top. You have you first can choose your welding cell. So later on, a user can have multiple welding cells. So he chooses the right cell. Then you can see, if you do live recording, you can have a look at your weld. You can have a look at the live welding data, and you can also implement like a red light system. Do I exceed a certain fume emission value? Then you would have red light, or if you are below the values, you would have the green light. And after your welding, you collect the data, and you can look at consumption data. For example, what was my energy consumption, what was my gas and wire consumption for the last 24 hours, for the last week, and for the last month. And you could also then compare different welding cells. So you really have a documented quality, and you have also documented safety for the welders and for those who are in your manufacturing area. For the marketing side, then later on, we created different welding cell concepts depending on the user type. We gave them fancy names like EduCell for people who work maybe more in the education area, or doing trainings, or have small workshops with daily varying tasks. We have a so-called work cell, where we have a higher number of parts to be welded. You can choose whether I want to have the doors in my cabinet, whether I want to place the robot, and so on. And the third option was a turn cell, where you could put in a loading table for loading and unloading components if you really want to have a very high productivity. And for those who cannot decide, we also build up a configurator where we can choose freely between all the different options. Yeah, we did achieve all this within the 6 months, and this was also only possible with the great support from our TWI mentor, Job Melton, and also with our business mentor from FundingBox, Mortisa Eftikar. Both gave very valuable input. They were always there for us. We had intensive discussions. So excellent from the technical side from TWI, but also very valuable input regarding business models and customer journey from Mortisa. So thanks again for this. So thank you for your time, and if you have questions, I'm glad to answer. Thank you.
Thank you, Emil. Thanks a lot. We actually do have a question comment from Joss.
Okay, thanks,
Yes.
Paul. Thanks, Emil, for your interesting presentation. And first of all, I'd just like to say that I think it's very topical, the environment, health and safety, a lot of focus on that now, and it's good to see innovations to help us meet these targets. I was just also going to say that one of the objectives of these presentations today is to guide those companies thinking of submitting a proposal for for the next call and to see how these projects worked. And for me, you know, I was very pleased to see that with the dashboard that you developed, I could sit, in fact, in my home as I'm doing in the UK, and yet still feel a part of the project. So that was great, and you know, just encourage those people who are going to apply for the second call to think about, you know, different ways of working to make these projects a success. So yeah, that's my comment. Thank you.
No, thank you. We realized this with a cloud solution, and we were also, let's say, I'm not as an IT and software specialist, but an engineer. I was surprised how easily this is nowadays with commercially available or also free cloud solutions.
Yes, I guess a thank you to Tim as well then for doing a great job.
Thank you. I will forward that. Thank you.
Okay, thank you.
Okay, thank you, Emma. Thank you, Ralph. And Ryan, hi. The floor is yours right now.
I hope you can hear me.
Yep, we can hear you.
Okay, very nice. So apologies for the mask, but obvious reasons. We're sitting with some colleagues in the room. Okay, can you see my screen?
For now, it's still a black screen.
Okay, I'm gonna do it the simple way. Here we are. So that would be this one. Okay.
Now we can see it. Yes.
Okay, nice. Now it's probably moved to the other side. Sorry. Yeah. Great. Can you see it?
Yeah, we can see it. We can see it.
Okay, perfect. So I want to present our pilot project called Promo ArcWe, process monitoring of arc welding. And we've been doing that using the acoustic emission from the process. And I want to give you, short starting point introduction. So where did we start initially before we kicked off with the project? Then give you our insights and our steps of development and results during the 6 months, and yeah, finish off just with a thank you. So we employ a acoustic sensor, so an air-coupled optical microphone, which is extremely broadband. So that is our unique selling point of our sensor, that we have up to 1 megahertz of frequency bandwidth for air-coupled sound. And initially, when we started, we only knew that the acoustic emission from the arc welding process is very rich in information, as you can see on this spectrogram picture here, the colorful one. But we didn't quite know exactly what information really is hidden inside. Also, we were employing a data acquisition unit that is actually not really tailored for this specific process, but for something entirely different. And we were just using some lab style mounting equipment. So these 3 points were really what we wanted to address and what we were able to really improve also, and that was really, really good. So first off, I want to start with the mounting. We've been able to construct something which attaches to the welding head. So we focused really on kind of robot guided processes. So we built something that could be attached to robot heads and ensures a stable and repeatable positioning. because that is, of course, essential when you do automated data evaluation, that you have always the same data acquisition and the same position. Still, though, you can do some adjustments on it, which is to increase the distance. Sometimes this process can be filled with a lot of sparks and a lot of debris, let's say. So depending on the conditions, sometimes a position further back has to be ensured, but still maintaining the correct angle. So that's what we realized here, and also it's possible to set the rotational angle of the microphone. So the microphone essentially would be placed inside here on the top here, where number 3 is written. So the first thing we addressed was, so which defects do we actually want to see, which are interesting for this particular process and for the users of this process, and which can we see with the cracks, excuse me, with the acoustic emission. And we ended up focusing on the defects of pores, of lack of shielding gas, and of cracks. So these are things that we could quite clearly detect with the rich information that we had. And so we focused on those ones. We performed multiple tests at the facility here at the Technical University of Vienna. We were able to move there. It couldn't go to TVI so easily. And here you see the robot, and actually this is still the kind of lab style mounting equipment, but that's kind of the position of the microphone where the data was captured. We did a comparison with X-ray images. Would actually be really interesting to have the software, the AI software from the first talk run over these. So these were done by TWI, so thanks on that note. And we compared our acoustic emission and also the visual with the X-ray images, and more to that later. Here, for instance, we showed the comparison of our signals to the defect, and what we employed was different criteria for each of the 3 defects mentioned previously. So each of these defects has a certain signature in a different frequency band, and that's what we found out there, and we tailored our algorithms to find these 3 defects in 3 different, actually 4 different frequency bands. And then we did a cross-check in the field to see how well does it really detect all the defects that we set up. So that was on the kind of defect catalog side. The second thing was to develop a software interface, a GUI, which enables us a direct feedback about these 3 defect types. And what you see on that software is, first of all, kind of the spectrogram. So the acoustic fingerprint, the entire process, that's very helpful just for kind of orientation. You then see the energy curves. So these are really the curves within the 4 specified frequency bands, which allow us to find the defects. And then here in this box, you get the output or the evaluation result. Again, here are our 3 defined defects, and you are able to adapt the thresholds according to your given process, and it allows you to directly see the defect detection rates, basically. So we did cross checks, and in that test run, we had 10 samples with pores or with moisture contamination, because that was how the pores are provoked. We had 10 samples with the lack of shielding gas, which results also in a very faulty weld. And of course, we had also the cracks. So with the moisture and the lack of shielding gas, it was quite easy to do like a direct defect detectability rate, because well, we know exactly when the defect was present, and we could then correlate it with our acoustic signal. With the cracks, it's actually not so easy to see them on the visual and the X-ray. We did, however, confirm kind of on an audible basis that cracks occurred, and we also detected cracks. So yeah, that's kind of already the sum up of the project. So I want to really thank, in the name of Xarion, the people from the WeldGalaxy project, especially Isabella from FundingBox, Ivars, who was our business mentor. Was a very helpful platform, actually, the Miro board, which we'll probably use also in other projects. Also thanks to Espen for the support on the platform, and of course Geoff and our mentor Bino for all the technical discussion and the support there. So yeah, thanks a lot, and I'm open for questions.
Okay, thank you, Ryan. We do have a couple of questions. The first one being from Lei. Hi, Ryan. Very interesting technology and nice presentation. A quick question, if you don't mind. In the real production environment, it's very normal to have a number of MAG welding robots working next to each other. Would the acoustic sensor get affected by those other welding operations close to it?
That's a really good question, and thanks for letting me address that. Let me pull up again the slide. Okay, so you see on our GUI the various energy curves, and they correspond to different frequency bands. So in general, the emission is very broadband, and there's a lot of high ultrasound content. And one of the nice physical properties about high ultrasound is that it does not propagate as far as low frequency sound. So like in the audible range, you easily propagate the sound waves many, many meters. But in ultrasound, actually, it's more on the centimeter scale. So when you focus on the high ultrasound frequency bands, you are quite robust against these neighboring MAG processes. On the low frequency band, you might actually get some interference. So that's why we tend to focus, if possible, on the high frequencies to exactly be robust against that mentioned effect. But one of these curves, actually, I'm not sure now which one it is actually focused on the audible frequency range, so kind of up to maybe 20 or 30 kilohertz. So with that one, we would have to check how influenced it would be from a neighboring machine, or if the same defect could actually be also evaluated in a higher frequency band. It just happened that in our setup, that frequency band, the low frequency band, was the most clear to bring out that defect. So we focused on that, and we didn't have any neighboring machines. But if that was the situation, we might have to look for a different frequency band, or yeah, adapt maybe the algorithm. That would be maybe something for the next phase in this project.
Okay, another question from James, and Lei is thanking you, by the way. Would this work with different modes of transfer, such as spray, short circuit, globular, pulse, etc.?
We have, so the process that we were looking at was a MAG process with a pulse modulation. I would have to get a welding expert now to explain to me the exact differences to the other processes, but it was a pulsed one and a MAG process. I believe possibly for some of the defects, for example, the cracks, there would be not much adaptation, because the cracks, well, are in their nature broadband, and we were looking at post-processing cracks. So in the cool down phase, I would believe that they are very much identical in any of the processes. The other defects, like the pores, there would have to be maybe some adaptation, because the pulsing was actually quite characteristic in the signature of this process. So if that's missing, maybe an adaptation would have to be done. But from other welding processes, we know that the emission in general, it's very broadband, so up to 500, 600 kilohertz, depending on the distance that you're positioned. So you do indeed have the frequencies available to do the analysis, but might have to be a little bit adapted.
Okay, thank you, Ryan. Then, Geoff, I think you also had a question.
Yes, thank you, Paul. Thanks, Ryan, for a very interesting presentation. I think my question follows on from the last one. Just to comment on the processes, I think that, you know, if you change the metal transfer mode in the MIG-MAG process, that's going to particularly change the, you know, the frequency, the lower frequency that you detect. And I guess it all comes down to the, you know, the frequency band that you choose.
Exactly. Yeah.
And indeed, you know, my question was about, as I say, a follow on, was to say, have you looked at TIG welding, and do you think your system will work for TIG welding?
We didn't look at it within this scope, but I would be quite positive that it would also work, because we've seen, well, it wasn't an arc welding process, but we know from many laser processes a lot about the acoustic emission from these kind of metal welding. Let's say it's that in that category. So metal welding processes, and I think it would also work, but we didn't look at it in that scope.
Okay, thank you. So this technique you also applied to laser welding, did you say?
Yeah, we do also. I mean, not this software, because it's tailored really for this special MAG arc welding, but with other acquisition units, we also focus on laser welding acoustic emission. Okay, well, as the TIG welding process has less your low frequency components, it's a more stable process than the big MAG process. It sounds to me as though it should work as well as with the MAG. So thank you. Yeah, I think it might even enhance it even more, or might be even more suitable then. It could well do, because it will remove a lot of the noise that you're getting in the MIG-MAG process. Yep. That's interesting. Thanks.
Okay, well, no other question. So I think the floor is yours, Geoff, for a few words of closure.
Okay, thank you. Would you like to remove the presentation that's up there?
Yep.
Conclusion. So I'd just like to start off by thanking the presenters, firstly, for keeping to time. I know there were some concerns that we had very little time to make the presentation. I'd just like to thank you all for keeping to time. I thought it was very interesting presentations. It was interesting to see that each of you adopted a slightly different approach to the information that you presented. And I think it was great because between you all, I think you covered all aspects of the WeldGalaxy program. So thank you very much for doing that. So just really in conclusion, to those of you planning to submit proposals, I hope you gained a lot of tips from today. I hope that these presentations have inspired you to put in a submission for the program, and we all look forward to receiving your proposals and working with those of you that are successful later on in the year. So thanks very much for joining us this morning, and good luck.
Thank you, Joe. Okay, well, thanks everyone for attending, and let us know any question regarding the call deadline 29th of April, and we'll be holding a last webinar on the 21st for any last doubts. Thank you.
Thank
Thanks,
you very
everyone.
much,
Bye.
everybody.
Thank you. Thank you. Bye-bye.
Bye. Have a nice weekend.
You too.